Hi guys, my name is Kylie. Today I will going to talk about our experiment named electrochemistry. So I'm going to do the introduction part. So first, what is redox reaction? So a redox reaction is a reaction that there are changes in oxidation number. So they can be divided to two half equations. One is oxidation, which is lose electron, and the other is reduction, which is gain electron. So the electron transfer actually is flow through the external circuit, the external wire in a circuit. So what is voltaic cells? So voltaic cells, also known as galvanic cells, that is a device to generate electricity through spontaneous redox reaction. So the oxidation and reduction occur simultaneously with the transfer of electron through external wires. This voltaic cell actually is made up of two parts of electrode known as half cells. One is considered as anode, which oxidation will occur, and the other one is considered as cathode, which reduction will occur. So we can use zinc and copper as example. So when the zinc metal immersed in zinc 2+ solution and the Cu metal immersed in copper 2+ solution, a saw bridge will connect these two half cells joined by wires. Actually, the electrons will flow from zinc to copper electrode. So actually we can see that zinc is anode, and while for the copper is cathode. So in the cathode, electrons are received by Cu2+ ion and reduced to copper. These two half cells also can write in half equations. So moving on to our voltmeter. So what is voltmeter? The voltmeter actually is measure the electromotive force, which is EMF, or cell voltage that produced by redox reaction. So the cell voltage depends not only electrons and the ions, but also the concentration of ions and the temperature at which cell is operated. What is standard cell potential? So the standard cell potential is to measure under standard condition, which is 25 degrees Celsius, 1 atm pressure, and also 1 molar of the concentration of electrolytes. Moving on to our concentration cell. So concentration cell actually is the study the dependence of electrode potential on ion concentration, which is a cell with the same electrode but different concentration of ions. By using zinc as example, so zinc metal is immersed in a cell with 0.1 molar of Zn2+ solution, while the other cell is 1 molar of Zn2+ solution. According to Lee-Chatler principle, the equilibrium will shift from higher concentration to lower concentration of zinc ion solution. So therefore, oxidation will occur on dilute side, while the reduction will occur on the concentration side. For the cell potential, which is E cell, is different from standard cell potential. It can calculate it by using Nernst equation. To sum up everything, in our experiment, we construct zinc to copper, zinc to magnesium, also zinc to scandium voltaic cell, and measure the cell voltage to determine the activity series of copper, magnesium, zinc, and scandium metals. The effect of the concentration on cell voltage is studied by measuring the cell voltage of zinc to zinc concentration.
Now I'm going to explain about the apparatus and also the chemical use in experiment 2. So the chemical use is magnesium chloride, zinc sulfate, tin chloride, copper nitrate, sodium nitrate, copper metal, magnesium ribbon, tin metal, zinc metal, and distilled water. The apparatus used is beaker, volumetric flask, voltmeter, dropper, crocodile clip, and also filter paper. Next is the procedure part. For the part A, determination of cell voltage. So in the part A, we will construct 3 voltaic cells using ZNCU and GZN and also SN-ZN metal combinations. So our goal is to measure the cell voltage and use the results to determine the activity series of the metals involved. So the chemical use in part A include 1 molar solution of magnesium chloride, zinc sulfate, tin chloride, and also copper nitrate. We also use metal strip of magnesium, zinc, tin, and copper. The apparatus include beaker, volumetric crocodile clips, filter paper for the salt bridge, and also distilled water. So we begin by preparing the metal chloride. Each metal strip is cut at a size of about 0.5 by 5 centimeters. Then each strip is polished with sandpaper to remove any oxide layer, ensuring it have a better conductivity and accurate voltage reading. So next, 50 mm of each 1 mole electrolyte solution are poured in separated beaker. These serve as a half cell of each voltaic cell setup. Next, to make the salt bridge, we soak a strip of filter paper in 1 molar of sodium nitrate solution. The salt bridge allows ions to flow freely between the half cells and also to complete the circuit. Now we construct the zinc copper voltaic cell. The zinc strip is placed in the zinc solution and the copper strip is in the solution. The sodium nitrate soaked filter paper is in position, so it dip in both beaker as a salt bridge. After that, both the strips are connected to the voltmeter using pip and then a positive voltage reading to confirm correct connections. So we record the cell voltage for the ZNCU cell and also repeat the same step for MGZN and SNZN and record the reading. So next part B, in part B we will construct a zinc concentration cell to observe how different ion concentration can generate an electric potential. 2 polished zinc metal strips are prepared. 1 beaker contains 1 molar zinc sulfate solution, while the second beaker contains a 0.01 molar solutions preparing by diluting the original molar solution. So we place each zinc strip in the specific beaker, then of course a sodium nitrate soaked filter paper as a salt bridge, allowing the ion to move in. So the zinc strip are connected to a voltmeter with because the concentrations are different, like 0.01, 0.1, 0.001 molar. A measurable voltage is produced, so we record this value for further analysis. So that's all for my introduction for procedure and also apparatus. Thank you. Now I'm going to explain about the apparatus and also the chemical use in experiment 2. So the chemical use is magnesium chloride, zinc sulfate, tin chloride, copper nitrate, sodium nitrate, copper metal, magnesium ribbon, tin metal, zinc metal, and distilled water. The apparatus used is beaker, volumetric flask, voltmeter, dropper, crocodile clip, and also filter paper. Next is the procedure part for the part A, determination of cell voltage. So in the part A, we will construct 3 voltaic cells using ZNCU and GZN and also SN-ZN metal combinations. So our goal is to measure the cell voltage and use the results to determine the activity series of the metals involved. So the chemical use in part A include 1 molar solution of magnesium chloride, zinc sulfate, tin chloride, and also copper nitrate. We also use metal strip of magnesium, zinc, tin, and copper. The apparatus include beaker, volumetric crocodile clips, filter paper for the salt bridge, and also distilled water. So we begin by preparing the metal chloride. Each metal strip is cut at a size of about 0.5 by 5 centimeters. Then each strip is polished with sandpaper to remove any oxide layer, ensuring it have a better conductivity and accurate voltage reading. So next, 50 mm of each 1 mole electrolyte solution are poured in separated beaker. These serve as a half cell of each voltaic cell setup. Next, to make the salt bridge, we soak a strip of filter paper in 1 molar of sodium nitrate solution. The salt bridge allows ions to flow freely between the half cells and also to complete the circuit. Now we construct the zinc copper voltaic cell. The zinc strip is placed in the zinc solution and the copper strip is in the solution. The sodium nitrate soaked filter paper is in position, so it dip in both beaker as a salt bridge. After that, both the strips are connected to the voltmeter using pip and then a positive voltage reading to confirm correct connections. So we record the cell voltage for the ZNCU cell and also repeat the same step for MGZN and SNZN and record the reading. So next part B, in part B we will construct a zinc concentration cell to observe how different ion concentration can generate an electric potential. 2 polished zinc metal strips are prepared. 1 beaker contains 1 molar zinc sulfate solution, while the second beaker contains a 0.01 molar solutions preparing by diluting the original molar solution. So we place each zinc strip in the specific beaker, then of course a sodium nitrate soaked filter paper as a salt bridge, allowing the ion to move in. So the zinc trade hypometer will voltmeter with
0.
because the concentrations are different, like 0.01, 0.1, 0.001 molar. A measurable voltage is produced, so we record this value for further analysis. So that's all for my introduction for procedure and also apparatus. Thank you.
An industrial process based on this principle is electroplating, where controlled redox reaction deposit metal onto surfaces. Factories use this process to coat many products such as jewelry with metals like nickel, chromium, or gold. The measured voltage becomes different from the theoretical value from contamination, where these unwanted substances can interfere with electron transfer. If the salt bridge has poor contact with the solutions, ion flow becomes restricted. This is slowing down the redox reactions and lowering the measured cell potential. As the dilute zinc topaz concentration increases, the cell voltage decreases because the concentration difference between the two half cells becomes smaller. A negative slope means that the line is slanting downwards as you move from left to right on a graph. In the picture, the blue line starts higher on the left side of the y-axis and moves lower as it goes toward the right side along the x-axis. This downward trend shows that when value of x-axis increases, the value on the y-axis decreases. The measured slope should approach the theoretical slope predicted by the Nernst equation, because the Nernst equation describes how E cell changes with ion concentration under ideal conditions. In a perfect setup, our experimental graph would match this predicted line exactly. However, some deviation causing the experimental slope to be a bit different from the theoretical value. A loose connections of the voltmeter can cause inaccurate readings because the electrical contact is unstable. This can lead to fluctuations in the measured voltage or even a lower voltage than the true value. Concentration affects accuracy because the cell voltage depends on the ion concentration in the solution. If the concentration is not exactly what is assumed, the dilution errors or when mixing can cause measured voltage will deviate from the theoretical value. Together, these two factors directly influence the reliability of the voltage measurement in electrochemical experiments. In battery operation, an external voltage drives a non-spontaneous chemical reaction, causing ions in a solution to move toward the electrodes, where they are either reduced or oxidized. In metal ion plating, electrolysis is used to deposit a thin layer of metal onto a surface. Metal cations in solutions are reduced at the cathode and form a uniform coating, which is widely used in industries for corrosion protection. Understanding how factors like concentration and voltage affect electrolysis helps students and technicians control plating quality and optimize battery performance in practical applications.
Assalamualaikum and greeting to doctor. So today I will be diving into the result of our experiment. So specifically, we will be comparing the measure of cell potential or E cell for 3 different cell combination against the theoretical value from literature. So for our experiment, we focus on 3 cells, which is zinc copper, magnesium zinc, and tin tin zinc. So we aim to measure the potential and analyze the accuracy of our result by calculating by percentage difference from the accepted standard value. So let's start with the first one, zinc copper cell. So in this cell, the oxidation reaction occur at the anode, where zinc is oxidized to Zn2+ and releasing 2 electrons. So the reduction reaction occurred at the cathode, where copper 2 ion are reduced to solid copper. So our experimental cell potential was measured at 1.123 volt. The accepted standard potential, or E cell, from literature is positive 1.10 volt. So comparing this value, we achieved the remarkable accuracy. The percentage difference was only 2.10%, and this small difference against our experimental setup was close to ideal condition, such as 1.0 m concentration and 25 degree temperature. So next, we move to magnesium zinc cell. This cell use a significantly more reactive metal, magnesium, as the anode. Here, magnesium undergoes oxidation to Mg2+. The reaction, half reaction, involves zinc ion being reduced to solid zinc. So notice the contrast in the theoretical potential. The literature value, E cell, is positive 1.61 volt, reflecting the high reactivity difference between magnesium and zinc. However, our experimental potential was significantly lower, measured at only 0.708 volt. This led to a large percent difference of 56.02%. So what could account for this large error? Factor like non-standard concentration, high internal resistance, or perhaps an issue with the surface preparation of the magnesium electrode of the magnesium are common culprit when using highly reactive metal like magnesium. So finally, let's look at the tin zinc cell. This combination features two metals that are relatively closer to each other in the standard reduction potential series compared to our first two examples. So in this setup, zinc is the more active metal, so it oxidizes to Zn2+ ion. So tin ion are reduced to form solid tin. So the theoretical potential E cell for this combination is positive 0.61 volts, which is the lowest theoretical potential among the 3 cells we studied. So our experimental result was 0.526 for this combination. Our experimental result was 0.526 volt, like the zinc copper cell. We achieved good accuracy here. So with a small percent difference of 0.91%. So these results against the condition for this reaction were also close to standard, and allowing the cell to generate potential very close to the theoretical maximum. So to summarize our finding, we successfully measured the cell potential for 3 galvanic cells. So the zinc copper, which is 2.10% different, and tin zinc is 0.91% different. Cells result with excellent accuracy, demonstrating reliable experimental technique and condition. So for the magnesium zinc cell, however, show a significant deviation, which is 56.02% different. This highlights the challenge of working with highly reactive metal and emphasize that a cell performance is extremely sensitive to real-world non-standard condition. Thank you.
Hi everyone, I'm Santia here, and I'm going to dive into something electricity, quite literally about electrochemistry, that we build electrochemical cells using metals, which are zinc, copper, magnesium, and tin. We didn't measure voltage only, but we have tested and measured how the ion concentrations affect the cell potential. So, in this experiment, we have used zinc and copper electrodes with different of concentration for zinc 2+ and copper 2+, which are 0.01, 0.05, 0.1, 0.5, and 1 molar. And also, we have used voltmeter to measure E cell to compare with experimental and theoretical voltage. The cell isn't just metals, but it also measures the concentration of ions. So, That's where the Nernst equation comes into in this experiment. Based on the table 1, which shows the result of zinc, the percentage is very high when the zinc dilution solution is too low, like 0.01 molar and 0.05 molar. At these low concentrations, the ions are not stable, so the voltage become inaccurate and giving some errors. At 0.10 molar, the percentage shows the smaller value, which is 8.12%. This is because the concentration is more stable, so the experimental reading is closer to the Nernst value. When the concentration difference becomes too small, like 0.5 molar versus 1 molar, the theoretical voltage becomes very tiny. Even small changes in the experiment produce a large percentage differences. So, for table 2 shows the result for copper. The percentage difference tells us how far the experimental value is from Nernst theoretical value. The percentage difference is small at very dilute and very concentrated conditions because copper ions are more stable, and the highest percentage difference appears at 0.1 molar, where the solution is still dilute, but copper deposition happens slowly, causing the cell to take longer to stabilize. When both concentrations are equal, the cell voltage becomes zero, and so does the percentage difference. Overall, the percentage difference is largest when system is low and smallest when copper ion concentration are stable.
In conclusion, this electrochemistry experiment allows us to understand how different metals and ions concentration affect a cell potential. For part A, we compared 3 different voltaic cells, which is the zinc-copper cell, the magnesium-zinc cell, and lastly the selenium-zinc cell. Based on the measured voltage, zinc-copper cell have the highest potential, which is 1.123 volt, followed by magnesium-zinc cell, which is 0.708 volt, and finally selenium-zinc cell, which is 0.526 volt. This trend matches the metal activity series, where a larger difference in reactivity between two metals produce a higher cell voltage. It also confirms that the more reactive metal act as the anode and undergoes oxidation. For part B, we studied a concentration cell, and even though the electrodes were the same metal, a voltage was still produced due to the difference in ion concentration. As the dilution increased, the cell potential also increased slightly, which agrees with the Nernst equation. And this shows that the cell voltage does not depend only on the metal used, but also on the concentration of ions in solution. Overall, the experiment helped us to see how redox reaction regenerate electrical energy, how the activity series predicts cell voltage, and how concentration differences can also drive an electrochemical cell. These principles are the foundation for batteries, corrosion control, and many other industrial electrochemical processes. And that is all from our group. Thank you.